Up to this point in our studies of trigonometry, we've picked up a knowledge of a few trig identities, notably sine squared x plus cosine squared x equals 1, that's the Pythagorean identity, and the tangent identity, the tangent x equals sine x over cosine x. There are quite a few more, and in this lesson we're going to be getting into a few more of them, and we'll get a couple more over the course of the next week. Before we get started, let's go and take a deep breath. And now let's begin. So as I mentioned previously, in this lesson, we're basically going to expand on the arsenal of identities that we have that we can use to transform trig expressions. And these identities are actually valuable in several different contexts. So one of them is something that we've already seen before, this idea of rewriting trig expressions in equations so that we can solve them. So some of the value of what we're doing is here in the trig unit. Right? The next one is we're eventually going to come back to calculus, and there are often going to be times that we're going to want to rewrite some trig integrand so that we can take some complicated integral. Integrals end up being, one of the more complicated things that we're going to do in calculus, and so having as many tools at our disposal to make them simpler is really, really valuable. And then a final value that we have for these things is finding one trig value given another trig value. There are more applications of this. I guess I just want to point out these double angle identities end up being, they're not quite as commonly used as the Pythagorean identities, but they're still fairly well used. So that you have a target of where we're going, by the end of this lesson, you're going to know identities for sine 2x, cosine 2x, and then at the very end for tangent 2x. Now, the concept of proof and a deeper understanding of the source of the math that we learn, since that's a focus of the Analysis and Approaches course, we're going to start this lesson by actually deriving an identity for sine 2x. And in this case, our strategy is going to be by finding the area of a triangle in two different ways. Now, on the Math HL Analysis and Approaches exam, I don't think that you're going to be expected to come up with a proof from scratch all by yourself, but it might be something similar to this, where they'll start you off with a diagram and then give you a few leading questions to get you through it. I actually wrote a question like that in the assignment tonight, so I hope that goes well for you guys. I'm going to try and sort of walk you through that process of what it looks like to prove something here for this identity for sine 2x. So let's go ahead and get started with this. Many proofs and demonstrations will start with a consider or with a let. Okay, so we're going to consider an isosceles triangle. So here I have an isosceles triangle whose top angle is 2x. Now you might wonder, why did I make it 2x? Well, in this case, the person that wrote this thing, they said, hey, I want you to think about this as being 2x. Okay, and the reason is they want you to think about the fact that you could split this triangle right down the middle and end up with two separate triangles whose top angles are x. And the reason this is valuable for us is we now have two diagrams, right, that are both kind of the same diagram. They're effectively the same triangle when you put them together. They've got the same area and all of that, but one of them has an angle of 2x and the other has angles of x, which is great because I wanted to find an identity that was going to let me get the sine of 2x. Okay, now I want to sort of give you guys some opportunities to practice working through this on your own. So I would encourage you to think, can we come up with an expression for what the area of this triangle is? Now remember, we've got two different formulas for the area of a triangle. Right? One of them is the one that we always used to know, that it's 1/2 base times height. But that one is really only useful if you have a right triangle. At some point, we learned a different formula for the area of a triangle that was 1/2 AB sine C, where C is just the angle that's in between two of the sides A and B. So if you remember that, if that's ringing some bells for you, I'd encourage you to think for a moment about how could you write an equation for the area of this triangle. Well, hopefully what you recognized here is that we could write that the area of this triangle is 1/2 of this isosceles leg, P, times the other isosceles leg, P, times the sine of the angle in between them, and that angle is 2x. And right away, we're feeling good about this because sine 2x is right here. That's the thing that I wanted to try and find an identity for. Okay, now I would like to ask you to again pause the video and this time find the area of these triangles. right? So come up with an expression for the area these two triangles are put together. Okay, so go ahead and do that now. So hopefully you noted that the area of one of these triangles would be 1/2 the base, which is q over 2, times the height, which is h. So base times the height. Okay, and then we remember we actually had two of those things, right? We have two of those things. So the area of this thing is actually just q over 2 times the height. Now the next thing we're going to do here is going to be a little bit sneaky, right? I want us to think in these triangles, what is the sine of x? The sine of x would be the opposite over the hypotenuse, right? So wouldn't it be q over 2 over p, right? And similarly, what is the cosine of x in those triangles? Wouldn't that be the adjacent side over p, so h over p? Okay. So now let's see here. If I were to move these p's over to the other side, I could get that q over 2 is equal to p sine x, and I could get that h is equal to p cosine x. Okay. Now, we're actually almost there, right? Notice that this area expression right here has a q over 2 and has an h in it, right? So couldn't I take this expression and put it there, and this expression and put it there? I could basically get that the area of this triangle is p sine x times p cosine x. And now we're almost done with this derivation. What I'm going to do next is I'm going to say, wait a minute, these things are both expressions for areas of the exact same thing. So that means that I could say that 1/2 p squared sine 2x, that's what I got from here, that is equal to p squared sine x cosine x. That's from here. I can divide both sides by p squared, and if I multiplied that 1/2 over, I would get that the sine of 2x is equal to 2 sine x cosine x. This is the double angle identity for sine. I know that took us like 6 minutes to walk through and to talk through, but this idea of being able to prove something, seeing where something came from, is a really, really, really important component in high-level mathematics. This idea of proving something is something that if you enjoy this is something that you can do in your math IAs. It's something that you can do in math extended essays. Like this is a part of the development of mathematics. So now that I've shown you where one of these is going to come from, I'm going to go ahead and go on and show you all of the double angle identities. We're not going to prove all of them. We're just going to prove this one, and I'll show you what the others are. So the first key point here is just me typing this identity for sine 2x that we just derived on the previous, earlier in the video. That sine 2x is equal to 2 sine x cosine x. And the next one, I'm not going to prove it here, but there are actually 3 double angle identities for cosine, right? They're right here, and all of them have applications in different contexts. They're all valid, and really the way that you move between them is by using that Pythagorean identity. If you were to plug, substitute the cosine squared here for sine squared, you'd wind up with that one. So that's kind of where those things are coming from. Now, just so that you're aware, all of these formulas are actually in the formula book that's provided for you on the exam. But there's a lot of value in you either memorizing or near memorizing these. They show up in a lot of places. I'll be totally honest with you. The trig identities that we're going to learn in the next lesson after this one are a little bit obscure. I don't know that even coming close to memorizing those is super duper valuable. You can if that's your thing, whereas the sine 2x and the cosine 2x ones really are quite valuable. They show up quite often. The first example that I have here is a fairly simple one. They're saying using the exact value of cosine 30, which is something that you guys should already know, they're asking us to show that the sine of 15 degrees is this thing, the square root of 2 minus the square root of 3 all over 2. Now, ideally what we want here is it looks like we want an identity that involves cosine and sine, where the cosine angle is the one that's doubled. So look back up above and see, do we have an identity that allows us to get the cosine of a doubled angle based on a sine? And we should. You should see up there that one of the cosine double angles is 1 minus 2 sine squared x. And here's the thing. This is an identity. Remember that what it means to be an identity is that it's true for every single value of x. These are identical to one another. And so what we can do now is we can say, okay, let's take this and let x be 15 degrees. If this is true for all values of x, then it'll certainly be true for 15 degrees. So when I plug in 15 degrees, I'm going to get the cosine of 30 degrees, 2 times 15, equals 1 minus 2 times the sine squared of 15 degrees. Okay? Now they wanted me to show that this is what sine 15 degrees is. So remember, I don't get to use this, but I know that this is going to be the answer. So my goal is to isolate this sine 15 degrees. I guess I'm going to need to isolate the sine squared, and then I'll square root it. So what is the cosine of 30 degrees? Cosine of 30 degrees in the unit circle is 30 degrees is over here. Cosine is the long one. So that's the square root of 3 over 2. So this is the square root of 3 over 2 equals 1 minus 2 sine squared 15 degrees. By the way, on show problems, it's always nice to be looking up at what we're trying to show. So as soon as I wrote the square root of 3 over 2, I was fairly happy because there's a square root of 3 right there. So I'm kind of feeling good about where this might be going. So next, I'm going to subtract that 1 over. So the square root of 3 over 2 minus 1. I'm thinking I want to get this with a common denominator, so I'm going to save myself a step and make this 2 over 2 minus 2 sine squared 15 degrees. So let's see here. Then it looks to be like I'm going to be dividing negative 2 to the other side. So I'm going to be doing a couple steps at the same time here. First of all, I'm going to put these two things together in the top. And then in the bottom, it used to be 2. Now it's going to be negative 4 sine squared 15 degrees. Now I'd like to square root both sides, but I'm not sure how I feel about this negative on the bottom here. So I'm basically going to multiply top and bottom of this thing by negative 1 to allow me to kind of get rid of that negative that's on the bottom. So when I do that, I'm going to wind up with 2 minus root 3, and on the bottom 4 equals sine squared 15 degrees. And the last thing I need to do is square root both sides of this. And so when I square root both sides, I get that the sine of 15 degrees is the square root of 2 minus root 3 all over 2. Now, you might be wondering, shouldn't there be a plus or minus on this? And I would say yes, and we do need to address why is this only positive? And I would encourage you guys to think for a moment, what do you know about the sine of 15 degrees? What do you know about 15 degrees? Don't we know that that's in the first quadrant? Since that's in the first quadrant, sine has to be positive. And so we write that really briefly. So this is a fairly simple example of how we might use one of these double angle identities. I don't know how likely it is that a question like this would show up in the HL exam. It could be a subpart of another question. I think something like this has a decent chance of showing up on the SL exam in case anybody's here watching this video in preparation for that exam. This next example gives us a picture of what might be closer to what's expected on the HL exam. I think these questions can certainly even get more complicated than this one, but this gives us a little bit more of the sense of what we might see there. This example says, find an expression for cosine 4x in terms of cosine 2x. Then continue this work and find an expression for cosine 4x in terms of cosine x. So just like we did in the previous problem, I want you to sort of look back at your identities, at your list of double angle identities, and see, do we have one there that gives you, like, look at this. This angle is 4x, and this is 2x. Do you see how that 4x is twice as big as the 2x? So that sort of makes us think, do I have something that lets me find the cosine of double some other cosine's angle? Right? And again, we do. Right? We have an identity that says that the cosine of 2x is equal to 2 cosine squared x minus 1. Right? Now, you might be noticing here, wait a minute, but this says 2x and I need it to be 4x. Indeed, that's true. But remember, this is supposed to be true for all values of x. right? So this is going to be a little bit awkward to write down, but what are we going to let in this one? What are we going to put in for x in order to work ourselves through this problem? Okay. Hopefully you're recognizing we could let x be 2x. And again, it's a little bit complicated that I'm using the same variable there. Don't get bogged down in it too much. If you're really, really bothered about it, just write an a here and write an a here. Just use some different variable here instead of x, and then you can let a equal 2x. At any rate, when I take this 2x and effectively plug it into both of these x's, I'm going to get cosine of 4x equals 2 cosine squared 2x minus 1. Okay? And the problem said, find an expression for cosine 4x in terms of cosine 2x, and I did it. Here it is. This is the answer to the first part of the problem. Okay. Now the second part says, now continue this work and find an expression for cosine 4x in terms of cosine x. So they want an expression for cosine 4x, that's already what the left side of this is, and they want that in terms of just plain cosine x. So is there a way for me to convert this cosine 2x in terms of cosine x? There is. I'd encourage you guys to try and finish this one on your own. Remember what this squared means. And I'll just take a brief moment on the side for that. Remember that what this means is it means the cosine of 2x squared. Like that's always what that notation means. Okay, so pause the video, see if you can work through finishing this problem out. So what I'm seeing here is that the left side of this thing is still just going to be cosine 4x, because that's what I'm trying to find an expression for. On the right side, I want to replace my cosine 2x, which is squared. I want to replace that with the cosine-based identity that I have. I'm going to use 2 cosine squared x minus 1. And this time I get to use x because this thing had already been boiled down to a 2x. Okay? And in a lot of ways, we can be done at this point. We could simplify further, but the problem said find an expression for cosine 4x in terms of cosine x, and we have it. This is cosine 4x. It's in terms of cosine x. I'm going to go ahead and simplify it the rest of the way out just so that you can sort of see what it might look like. But that's it, right? So if I wanted to go further here, I could have like 4... Let's see, if I was moving this in, 4 cosine to the 4th x minus 4 cosine squared x plus 1, and then there's the minus 1. Then I'd have to distribute this 2 in. That would give me 8 cosine to the 4th x minus 8 cosine squared x plus 2 minus 1, so plus 1. So this is my expression for cosine 4x when it's fully expanded. I might mention, by the way, that it feels to me like there's potential for an IA here. If you guys really, really like this stuff, we have an identity for cosine 2x. We've got one for 4x. I bet we could find one for 8x. I bet we could find one for 16x. Is there a pattern that happens there? If so, what it is? What is it? How could we prove it? In tomorrow's lesson, we're going to figure out how to get identities for like cosine 3x, cosine 5x, cosine 6x, everything in between. I wonder whether there are patterns there. I literally don't know. So that's something that you could investigate, something that you could look into. It wouldn't be easy, but if this is something that you're really liking, I want you to know that this is the kind of skill that we're trying to build in this Math HL course. In this next example, we're going to look at how the trig double angle identities can help us to solve equations that we might not otherwise be able to solve. So in this one, 8 sine x cosine x equals 1, it doesn't look a whole lot different from the problems that we handled in previous lessons. But as we look closer at this thing, like if I subtracted 1 to the other side, I can't... Okay, there's no way to factor this thing. We're just sort of stuck. So I would encourage you to, pause the video, go back and look at all the trig identities that we got in this new lesson and see if this looks similar to any of the ones that are there. Hopefully you noticed that we've got a trig identity there it was the one that we derived, right? The sine 2x equals 2 sine x cosine x. Sine 2x equals 2 sine x cosine x. This is really similar to that. Like if I were to look at the left side of this thing as 4 times 2 sine x cosine x, then I could replace that 2 sine x cosine x with sine 2x. So 4 sine 2x equals 1. And now this problem should be really, really similar to some of those problems that we did probably about a week ago now. So I hope that this is one you guys can go through on your own. Remember that for these problems, when you've got something inside that's not just x, when the argument is different, we do need to think about how that changes the bounds and how we're solving the problem. So if you feel comfortable doing that on your own, pause the video and try it. If you'd like to follow along, then here we go. So the first step I'm going to take is I want to get this trig function alone. So I'm going to divide this 4 over. Right? So the sine of 2x will be 1/4. Okay. My next step here is I really, really want this thing inside to be just a single variable. So I'm going to let m be 2x. Okay, so that'll give me the sine of m equals 1/4. Okay, but then my bounds up here, I originally had bounds that were negative pi less than or equal to x less than or equal to pi. Okay, and so what I want to do now is I want to change these things into m bounds. Right, so I can take this x bound and plug it in right here. So when I plug in that pi, I'm going to get negative 2 pi is less than or equal to m is less than or equal to, and when I plug in pi for x for this thing, I get 2 pi. So I've sort of transformed the problem from being in terms of x with these bounds into being in terms of m with these bounds. From there, I'm going to go ahead and go through and solve. M will be the arc sine of 1/4. When I solve this on the calculator, I find that m has to be 0.253. Or, remember, we can also get pi minus that answer, pi minus 0.253, which gives me another m value of 2.89. Remember, these aren't final answers because these are just in terms of m, but I've got these two answers. Now remember, at this point, we do need to think about, we found the primary solution for sine, we found the secondary solution. We could also add or subtract 2 pi, because that's the period length of sine. But if I added or subtracted 2 pi to these, I would go outside of these bounds, which is not what I want to do. So we're confident that these are the only two answers. Now we take these things and we need to convert them back into x, so we go back up and we use this conversion factor that we had originally used to get us here, right? So now recall that m is 2x, and that means that x is m over 2. So I basically just need to take these answers and I need to divide them by 2. So if I take the first one that I got and divide it by 2, I get 0.126. One of my answers, and then the other one, if I take and divide by 2, I get 1.44. You'll notice that both of those are on the bounds that were given, negative pi to pi, and that should happen because we made sure that the m's stayed within their bounds. Okay? So this, again, an example for us of how we can use these double angle identities to convert or change or transform an equation into something that we're able to solve. All right, so I've got just one last example for us. Solve the equation cosine 2x equals cosine x on the interval from 0 to 2 pi. So as I've asked you to do before, I want you to pause the video and I want you to go back and look at your identities for cosine 2x and see if you've got an idea for which one of them is going to be most useful in the context of this problem. So hopefully your thoughts on that are that the best one to use is the one that converts entirely into cosine. Because if I pick the one that converts entirely into cosine, this equation up here is going to be all in terms of cosine. And it's all going to be in terms of cosine x, none of this pesky 2x stuff. Right? I forgot to mention at the beginning of this really can't be solved right off the bat because these have different arguments inside. Okay, so I'm going to take this and I'm going to plug it into this thing and then we'll work through the rest of it. So when I plug this in, I wind up with 2 cosine squared x minus 1 equals cosine x. As we've done before, I'm going to move everything over to one side so that it's equal to 0. Make it easy for me to solve by factoring or any of my other methods. I'm going to encourage you again, pause the video here, make sure that you can finish this out on your own. Here we'll let m be cosine x, just so that we can really, really plainly see what this is going to turn into. This becomes 2m squared minus m minus 1. And here we hope that this factors 2m m minus 1 and plus 1. Let's double check and make sure that that works. This is positive m, this is negative 2m, that gets me negative m here. Yep, those things all work, which means that my solutions here are either that m is negative a half or that m is 1. Okay, but m used to be cosine x, so we're going to bring that back in now. So we now have that cosine x is negative a half or that cosine x is 1. Okay, remembering the bounds that I'm working with here, I'm now gonna go forward and solve these equations down here. Turns out these are both unit circle values, so I can just do the inverse cosine of negative a half. And so we're thinking to ourselves, what angle gets me a cosine value that's negative a half? So if you're sort of thinking about your unit circle, negative a half for cosine, that would be up here and it would be down here. Right? So this one up here is 2 pi over 3. So great, we found that one of our x values is 2 pi over 3, and our other one would be negative 2 pi over 3. But we don't actually want that one because, if my memory serves me, we were going between 0 and 2 pi here. So I would take this other answer and add 2 pi to it to get it into the right space for me. So this one gets me 2 pi over 3, and 4 pi over 3. And for this other one, I'm going to need to do the inverse cosine of 1. Well, the cosine value of 1 only happens over here. That happens at 0. And we could also add 2 pi to that to get 2 pi as our other solution. So there we go. We found our 4 solutions. These are the 4 solutions. This video is already running pretty long, so I don't have any more examples after this. I just wanted to mention all of the work that we just did with sine and with cosine having double angle identities. Tangent also has a double angle identity, and this is what it is. So if you want to find the tangent of double an angle, you do 2 times the tangent divided by 1 minus, and then take the tangent to the original angle and square it. So you may see some problems come up with this in the assignment tonight, or as we move forward and continue to review the things that we're reviewing. Hope that all made sense. As always, let me know if you have questions.